Okay, so in this video, we'll look at the maximum subarray problem on Leetcode and how we can solve this in Rust with a variety of different solutions. And then at the end, we'll look at how we can benchmark these different solutions to kind of see just how different they are in kind of execution time performance. So let's first of all read the question. So in this case, we are given an integer array of numbers and we'd like to find the contiguous subarray, which has to be at least one number large, which has the largest sum, and then return that sum. So we don't actually return the subarray itself. So if we look at this example given here, we can see there are also negative numbers, and in the end we want the output 6, and in this case the subarray that gives us that answer is 4, minus 1, 2 and 1, so if we sum these numbers together we get 6, and this subarray has to be contiguous in the initial input. So let's start out by just kind of writing the simplest solution we can think of and checking that this works for this test case and kind of a few other test cases we can think of, and then we'll look at different solutions. So let's start by creating a new Rust project. So we'll call this max subarray and we'll make it a library crate. Okay, so we now have that. So let's cd into this max subarray package, and we can kind of view everything here. It's a bit bigger. So the reason this is made a library is that later on for the benchmarking, basically it's easy to share the code. So, since we'll use kind of unit tests to test all of the examples here, we don't actually need to run it as a binary either. And then, if we did want to add a binary, we could easily add that to the library by kind of creating a separate binary file. So let's load this here. So here we have our code, and here we have kind of a unit test. Now let's start by setting up our unit test. So the kind of harness inside of Leetcode actually uses this struct solution. So we want to have that same logic here. So in this case, we'll create a public struct so we can use it later on for benchmarking, and we'll then just copy this implementation over. Oops. So this is basically the same kind of setup that we have in Leetcode. Now let's work on adding the test case. So here Rust already creates us kind of one example. So let's just rename this to kind of Leetcode example. And in this case, what we want to do is call solution max subarray and pass it this array, which will be vec 4 minus 2 1 minus 3 4 minus 1 2 1 minus 5 and 4. So in this case, we're actually declaring a vec literal. So we can pass that directly without having to kind of create it separately. And then we just pass it the vector we're given inside of Leetcode and call this. And we want to check that this matches 6. And now we get, so I'm using COC in Vim and the Rust analyzer. And so this is how I get kind of the error messages directly in Vim as I compile. So let's just make this always return 0 for now, so these errors go away, and then check what this error is. So failed to resolve use of undeclared module or type. Because here we need to actually import everything above. So if you're a superstar, cool. So this is basically saying import kind of everything inside this file. So now we can see the struct that we declared above. So with that in mind, we should now be able to run this test, and it will fail, and it fails because it returns 0 and we expect 6. So now our unit test is working, so let's add kind of a few additional tests. So this was kind of the example they've given, which covers like a lot of logic here. Let's also check the case where all the numbers are negative. And so if all the numbers are negative, we want kind of the smallest negative number. So for example, if we do this, then in this case our smallest negative number is -1, and so we'd expect that to be -1, and let's set this to kind of negative example, something like this. And maybe let's just add kind of one more trivial case of, for example, if we have just an array with kind of one number, then we expect that one number back. So let's just something like this here. Okay, cool. Just call this 0 example. Okay, so these should be kind of enough test cases to get started. So now let's think, what would be the absolute simplest way of solving this problem? So basically we want to check kind of each subarray inside this array and find kind of which one has the largest sum. So the kind of naive way of doing this is just to generate every single subarray. So kind of use like a nested for loop to look, okay, first of all, just at like -2, then -2 and 1, then -2, 1, -3, and calculate the sum every time and store the best one. And then, move across here and do the same here. So let's see, how can we implement this logic? And then we'll kind of reason a bit about what the runtime of that would be. So the way we can do this is, if you think about it, we have kind of the start position, like here in our array, and then what we're doing is we're kind of looping for every start position, loop over all possible end positions. Now, all the end positions can basically be kind of going from the start position. You can't go kind of backwards, going forward through it. And the start position can be equal to the end position, in which case we have only that element. So if we were to implement this, we can do it with kind of 2 for loops. So let's do this. So we start with our kind of start, let's call it start instead of I. So for start in 0 to nums.length. So this is the start one, and then we'll say for end in start to nums.length. So this goes from 0 to the end of the array, and then we go, okay, for each case there, go from that element to the end of the array as well. So that's going to give us kind of the 2 indices that we want. And now we just need to actually get the subarray. So we should also start by defining kind of our, like, let best equals. Now here we have a check, like, you might think immediately, okay, we make this 0, but actually all our numbers can be negative. So this should actually be the minimum value for an I32, which in this case is I32 min, which would be some negative value, which is kind of the most negative value we can store in an I32. And bear in mind that Leetcode told us that all the values are of type I32. So with that in mind, we can now just check, okay, let's get this array, sum it, and check, is it greater than our best? And if it is, update the best. So to do that, we can take our array nums. We go from start, and we go up until end, but note we include the end index because, for example, they can both be 0, and we want to make sure we still have that initial element. And then we just sum that. So in Rust, that means making it an iterator and then calling sum. And we can say this is kind of our value. Let's just call this S, for example. And then we can say if S is greater than best, then best equals S. And then at the end of all of this, we will go here and we want to just return best. And these should be there. Okay, so this looks good. So now let's run this. And okay, it looks like everything worked. Let's just make this a bit bigger so we can see. And we see we get okay in every test example. So this seems to work. So now let's think about, okay, what's the computational complexity of this? So if our initial array, so the only kind of argument we have here is the initial array. So as the initial array gets bigger, what is the effect on this algorithm? So in this algorithm, we first have to go through every single index, right? So that gives us kind of one sweep, which would be kind of, if this was n elements, so let's actually write this down. So if we have n elements in nums, then we start, and first of all we do kind of one sweep of n for the start. Then for each end, we go again through every remaining n. So that's also kind of on the order of n, right? It's going to be kind of n minus 1, n minus 2, and so on. But that's on the order of n in terms of, getting rid of that constant factor. So that makes that n times n, which is n squared. And now this sum as well also has a cost, because each time we call the sum, we're adding repeatedly kind of every element inside the array, right? So if you imagine when we first let's go here. So we first do minus 2, then when we do the next kind of subarray, we do minus 2 plus 1, and then when we do the next subarray, we do minus 2 plus 1 plus minus 3, and we kind of repeat in this calculation, like we recalculate minus 2 plus 1 again. And so in terms of number of operations, this is also on the order of n, right? Because as we're increasingly going into the array, we're doing more sum operations. So this also increases with respect to n, and so we're going to end up with something kind of on the order of O of n cubed. And later on, we'll try and kind of plot this in the benchmarking program and see kind of what this looks like. So let's mark this as kind of the n cubed solution. But this works. So now let's kind of just copy the solution and see, like, how can we do better? So without kind of looking at the details of this specific problem, like one issue we had is that we were repeating the sum. We were kind of repeatedly repeating steps, right? So like we do minus 2 plus 1, and we calculate minus 3, and then when we calculate kind of the window including up to 4, we do minus 2 plus 1 plus minus 3 again, even though we've basically already calculated this number. So one trick we could do is to kind of cache this calculation, right? So we remember, oh, we've already calculated this, so actually we only add up pairs of numbers each time, and so that reduces the number of operations, again, on the order of n, at the expense of using this memory to kind of cache these intermediate values. So let's have a look at how we could implement this in a simple way that will be kind of costly in terms of memory. So let's get rid of this and get rid of this. So in this case, what we'd like to do is basically store those intermediate sums. And if you imagine one way we can do that is to kind of store this in an array as we go. So let's imagine we have like 0, 1, 2, 3 as our initial array. Then as we go, we'll store kind of the sum of the previous elements. So here we'd have 1, and here we would have, so this is just 0, 1, 2, 3, and then here we have 2 plus 1, which is 3, and here we'd have 3 plus 2, which is 5. And now as we go across here, we do the same thing. So here we'd have kind of, what would 0 plus 1 plus 2, which is going to be 3 again, and here we'd have 1 plus 2 plus 3, which is going to be 6, right? And then at the end, we'll also have 6 just by virtue of the fact that the first number is 0. So here you can see basically we're storing kind of these windows, right? So instead of having to calculate the window every time, now when I want to calculate kind of this element, I realize this is just 3 plus 0, right? Or if I want to calculate this one is 6 plus 0. And the same kind of applies to all of these intermediate calculations. So when I'm doing like 5 is 2 plus 3, we have to calculate that from the start because it's a pair. But when we get to 6, we can realize that 6 is 3 plus 3, right? So it's like the last, like we can use the fact we already had the pair sum here. So that's basically the trick. We kind of cache these intermediate sums, and we use that in our algorithm to not have to repeat these sums every time. So with that in mind, let's kind of implement that here. So we still need to do one loop. So we have to go through every element. But when we do it, we want to build up this array. So let's start by kind of actually creating this array. So notice here, this is like a triangular array, right? Because this array would be symmetric, but we only care about these kind of upper right elements. So one thing you could do is flatten this out. so that you use less memory. Because, you know, imagine if we create a square kind of matrix here, we have basically all these wasted elements. But in order to keep this simpler, we will just have those wasted elements. So now, in practice, you could kind of re-implement this, just having like a flattened array that represents this triangular array here. So let's try to actually implement this. So let's call this kind of sum arrays. And here we use a vec of vex by 32. And so let's first just start out by kind of making them all zeros. So we have vec, we have 0, and then we have however many elements we have. And then this will also be again however many elements that we have. Okay. Now we have the same problem that we're not returning anything here, so. Because this is called Leetcode, right? Okay, so now we get something that looks okay. So now we actually just have to kind of make this work, right? So let's start by actually filling this array sum. So at the moment we have just a 2D array of all zeros, and we need to start filling this with our sum. So first of all, we go through, we say, okay, for start, we want to just, so that the first row is always going to be just the elements. And for the first element, we only have that. So what we actually want to do is go like for kind of row in 0 dot equals start. So this is saying like kind of like on the first one, just give us 0, and then we're going to get 0 and 1, and then we're going to get 0, 1, and 2. So as we go further in, it will give us kind of access to more rows we're going to fill in. So with that in mind, we say that array sum. So bear in mind, these arrays it's going to be like row first, right? So we want to put row here, and now we're indexing inside, like going across the columns. And so we're going to say this. So row start. Well, actually, one thing we should do to make this a bit easier is to start kind of from 1 and just actually set this straight away. So, and this needs to be mute as well. So let's just try and solve this here. So we want array sum 0 to just be equal to stop close. Okay, so we basically saying set the first row to be equal to a copy of the kind of numbers that we're given. So now that means we can start kind of only filling in from here, and so we're going to go through each row, and then we also need to fill in from the second row, of course. And so we only need to fill from the second element because we have kind of no additional rows in the first one, and we only need to fill from the second row because we already have the first row filled. So with that in mind, this now allows us to basically calculate this using just the index of the row in the start. So we don't need to have like a special case for the first row. So with that in mind, the second row is the sum of the pairs. So this comes from 0 plus 1, which gives us 1 for this pair. And now to get this element here, like if we want to just add on the 2, we just do 1 plus 2 gives us 3. And now 3 represents this sum across here. If we want to add on the 3, we just add on the 3 to this, and that gives us 6 straight away. But in terms of filling this as we go through, kind of what we have available as we kind of iterate through our array, kind of on 1, the only things we can calculate are like all the things up to this. So we can calculate just the 1 itself, which is obviously already here, and then 0 plus 1 as we fill in this one. Then at 2, we can calculate just the 2 itself. Then we have 1 plus 2, which is just a pair, so we fill this in here. And then we have 0 plus 1 plus 2, which is going to be kind of this one, so like one to the left plus the new value plus here, and this holds true. So it's like this one plus this one equals kind of the new one to fill in at each row. So let's try to fill this in here. So this is going to be, so imagine we're on the second row, so it's going to be like 0 plus 1 plus 1, and then when we're kind of on the third row here, this is 0 plus 1 plus 2, so then it's 1 plus 2. So it's like 0 plus 1, here 1 plus 2, here 3 plus 2. So it's the original. So it's the original number here, which is going to be kind of num's start. And then to this, we want to add what is like above us and to the left. So that's going to be array sum, row minus 1, and then start minus 1. Now, here we can use something that, at the end of this, what we want to return, so this effectively calculates us a sum for every subarray will be inside this matrix, and what we want is the highest one. So actually, as we fill this, we can also calculate the greatest one that we've inserted, and then just return that, so we don't have to eventually kind of do a lookup on this again afterwards. So we already have best here, so what we can also say is, let's actually just take this as a variable quickly. So let's say let ln equals this, and now we set this to be ln, and then we can say if ln is greater than best, then set best to be ln. Otherwise we just carry on. So let's check if this works. There were no errors from Rust Analyze, which is always good, and let's test that. Okay. We get some error messages, and okay, so clearly like best isn't being updated, so for the 0 case and for the negative case. So for the negative case, it just need to get -3, and for this case we're just not updating it at all, right? So this is the minimum value of the I32. So let's try to resolve these cases. So the reason is because we didn't consider also, like if you imagine this works for this inner part, but we didn't do this for the kind of initial array. So we've done this for all of the sums, but actually if the minimum value, maximum sum rather, is actually a single element, we don't consider that here. So we need to add in that case as well, right? Because if it was just one of these ones, this was never kind of considered because we did this clone trick to fill this in straight away. So we also need to say, so since we're going to iterate through it anyway, it doesn't really cost us anything to iterate through this one array again in terms of like asymptotic cost. So let's just do that. So we can say best equals array sum dot min dot maxi. Well, I'm going to erase some here, so this should be nums. And since it's Imprint's copy, so this was giving us a reference, right? It's giving us a pointer to the maximum element. We just want the element, like the value itself, but since these are I32, say implement copy, so we can just dereference directly and take a copy. So that's fine. So let's run this, and now this works. Okay. So let's think about a bit about kind of what we've saved here. So here, the only thing we've changed from our kind of initial solution, as well as using a lot more memory, is the fact that we don't kind of repeat these sums. So each sum now is just a sum between pairs. We only ever sum pairs of elements. So that's an improvement, right? That reduces the amount of work we're doing at each kind of inner step of this effectively a nested for loop, but it doesn't really solve kind of a lot of the computational costs, right? So you can imagine, okay, we get rid of one kind of round, like this last round of n disappears because we're now only summing a constant number. We're doing a constant number of operations, which is the sum of the pair. So let's write that here. So here you can imagine we first do this n, we loop through the whole thing, and we then have to fill in every row, but then we actually do a constant number of operations per row, like per element we just do the sum of a pair. So this now comes kind of O of n squared. So this is better, but bear in mind we're also using O of n squared amount of memory, especially in this case where we're allocating kind of this full square matrix and then only using half of it. So this is not great. Ideally you could at least improve this, but the benefit of this solution and why it's important to learn is that this works for any operation that's associative. So we'll actually now look at a much faster trick and the optimal solution to this problem that can do it in a single pass, but it uses kind of attributes specific to this problem. Whereas this trick of building up an intermediate array and caching the results can be used in a whole load of different scenarios. So for example, instead of the sum, this could be like any associative operators, things like a product would also work, or like any sort of function you have that has these properties. So it's something that's good to kind of keep in mind, especially as you might deal with kind of more complicated problems. So let's do that, and now let's move on to kind of an even better solution. So cool. So with that in mind, let's look at this. So let's just delete everything. And okay. And let's read the problem carefully. So we know the subarray has to be contiguous, and we want the largest sum. So there's a few kind of things here, right? Like if it's negative, we know we just want to give the smallest negative value, like the negative value of the smallest absolute value. If it's kind of positive, then we just want to keep summing, right? Imagine if all the numbers are positive, then the best solution is just the sum of all of the numbers. There's kind of no special trick. So what gets tricky is when you have the negative numbers interspersed between the positive numbers. So imagine if we start from the left-hand side, what we can do is just keep summing, right? And okay, so we reach -2. Is -2 better than best? Yes, it is. Set best to -2 straight away. We can then sum -2 and 1 now. Then we get -1. Is -1 better than what we already have? Yes, it is. So replace what we had. Then we get -2, 1, and -3. And now in this case, this is no longer true, right? This is no longer better than what we had. So we can now basically get rid of this entire thing, because if we add on negative numbers to whatever we have on the right hand side, like if you imagine we basically have what we have on the left hand side and what we have on the right hand side, because the subarray has to be contiguous. So if this left hand side is negative, then whatever I add to it on the right hand side, I'm only going to make that number smaller. So whatever number I have on the right hand side, the number on the right hand side will become smaller by adding this negative number onto it, which in this case would be -4, right? So we're better off just discarding all of this. And so the moment we get a negative kind of left-hand side, just discard it. So if -2 is negative, well, get rid of it and look at one. Update best if it was better, just in case we have a case where they're all negative. But then discard it and look at only the other elements. So then we start from 1. Okay, 1 was better, we update it. We do 1 -3. Well, now it's negative again. So we throw that away and start from 4. Well, 4 is positive. And then we can go through like this. Using the cumulative sum until it becomes negative, and then throw away that subarray when it does. So that's kind of the approach we'll use. So let's look at how we can implement that. So we're going to need kind of a cumulative sum. So let's say let each sum equals 0. And then we just want to kind of loop through the array once. So this will basically give us each number in the array. So what we want to do is say let So sum plus equals n if sum is greater than best equals sum, otherwise we do nothing, and then if sum is less than 0, then set sum back to 0. So that's basically this trick. Bear in mind, we only need to return the sum. We don't need to return anything about the elements, the position or anything. So discarding this side is basically setting the sum to 0. And that looks good. We return best here and we update best there. So let's save that. Okay, Rust Analyze doesn't complain. And now we can test this again. Okay, and they all pass. So that's good, right? So let's look at this again. So in this case, we do only one pass through the array. So that's O of n, and then we're just doing one sum for each element. And then we have kind of two comparisons, but that's just a constant number of operations, right? So this is actually O of n, and this does it with just one single pass. So this should be the best solution to this problem. Okay, so now we've kind of done all of this. Let's look a bit about how we can. So I've stated the kind of computational cost of these different implementations, but maybe we can actually compare and plot these. So in Rust, we can do this with a crate called Criterion, which will give us kind of nice graphs. And we will also need to generate some random test cases in order to be able to produce these graphs. So we'll also add rand here. And now we can see here, so this is the code for the benchmark. So basically we generate a random vector, fill it with elements between minus 100 and 100. Then we run each benchmark, we give it kind of 5 seconds time where it warms up so you don't lose time on initialization, things like allocations. And then we give it only 10 milliseconds to run each load of tests. So, and the main reason for that is so this actually finishes within like 2 minutes instead of taking hours. Especially on these kind of slower functions. If we gave it a large input, it would take a long time to run because this runs this many times to generate statistics. So we then run it on this set of sizes, so from 1 to 1,000 elements, and we call that basically for each different implementation, which we've labeled as n squared, and n cubed, and then we just tell Criterion to run this. So you can see it's now running here. You can see the time it's taking for each case. So, and you can already see kind of the differences between the run times. So as this gets kind of slower, kind of as the input size increases, this should become kind of much more marked. And we can see, for example, like the n case, even where at like 150 elements, is still in nanoseconds, whereas the other implementations are now running in microseconds. And you see we're now actually getting complaints that it can't finish 10 measurements within the time given. But we're not going to increase the time because that will make it kind of even slower. So now that's Criterion finished, and we can actually see Criterion's output here. So go to target, Criterion, report. So this is the output, and we can load this here, and now we get a nice plot. So, oops, the dark theme is actually making this difficult to read. Let's turn it on. So here we have n squared, and the n cubed implementation. We say, okay, this is the size of the input. And basically, as we increase the size of the input, now we know that this has to be linear, right? There's no way this can be kind of like a constant time computational complexity, given the fact we have to scan every element. But still, imagine the kind of coefficients on this are so low that we basically will see this almost as a constant line up to this amount of inputs. Whereas the other two, you can really see this difference. Like the n-cubed one, our most basic solution, rapidly begins to grow to the point where this is much, much, much slower. And the same is true of the n-squared solution as well. Bear in mind, what we don't see here is the memory usage, which the n-squared solution is also using kind of n-squared memory effectively. So, we're allocating that much more memory every time we increase the size of the input. So, yeah, hopefully this video has kind of shown you how to solve a problem. And in fact, let's go and actually submit this here. So, so let's actually submit our solution here. So we can copy this solution. And so this is Max Subarray solution, and we need to close it. So let's just submit that, and hopefully we don't get any. Hopes this should be so I think this depends on. So it's strange because this works locally, but I think here this needs to have the actual standard. Yeah, let's actually see what's going on. Okay, now we see success. So for some reason it didn't work in Firefox, but anyway, so at the bottom we say this worked, and we get kind of a very fast runtime, very low memory usage. So yeah, hopefully this has been useful to see kind of how you can solve a problem like this, and kind of the strengths of different implementations and how you can compare different implementations. So really, as you work through different problems like this, I'd really recommend coming up with the most basic solutions and then seeing how you can kind of improve those, and then ultimately benchmarking your solutions as well. So you can see in practice what is faster, because there's a lot of different things that can impact the real world performance of these algorithms. So what we consider to be theoretical performance might not always be reflected in the real world due to things like cache misses and how much kind of contiguous memory you can fit in your CPU cache together, which, for example, some algorithms, if you have kind of every element stored separately, something like a linked list, then you kind of lose out on that feature of your CPU, and in practice your algorithm would run slower than you might consider just kind of looking at the theoretical analysis. So that's something to bear in mind as well. So hopefully this has been useful. As always, if you'd like more videos like this, please subscribe to the channel. And if you find any kind of issues in the implementation, let me know in the comments. Thanks.